Ladies and gentlemen, welcome back to another live stream. So in this live stream, we're going to be trying vanilla JavaScript coming from low-level languages like C, C++, Rust, etc. So I haven't tried like JavaScript for a long while now. I mean, since I've been young, I was like 13 years old, and it was like my first time trying to get my hands on like HTML, CSS, and JavaScript programming. So that was the only, and it was like maybe, I don't know, 10 years ago, or I don't know how much. I didn't go too far into it though. But today we're gonna try vanilla JavaScript. And hello, Theo Paris. Welcome to the live stream. Welcome. I'm also gonna be trying a little new AI workflow. Instead of letting the AI agent do the coding for me, which just kind of suck and just waste my time. I end up learning nothing. I actually just made the AI research, read examples from all sorts of places, and etc. And it basically just made a tutorial for me, and we're gonna try to follow this tutorial today in the live stream here. So I'm just live streaming this just to share my journey, pretty much. Nothing fancy. All right, so let's open up this. Wait, not this. Hold on. I guess let's just. Oh, I already have it here. Okay, cool. So I just have this little folder in my. Wait, where's VS Code? Let's just open up VS Code. And let's see. All right, let me open up the chat on my phone. Hold on. Chat. Let's see. Okay. There's the chat. Let's see. All right, cool. Okay, I have the chat in front of me. Sick. Now let's see what we could do. All right, so let's open up a folder. And I got this website folder on my desktop. It doesn't have anything fancy. It just have, just an index.html, which contains a little page right there, and a tutorial, an MD tutorial that is created by the AI, and we're going to be following it together. So open preview to the side, open as preview. Okay. So we could do just this, and obviously we're only going to be using one file, so we're just going to do this. And okay, where's the file though? There you go. All right, sick. In fact, there is even, I believe, like we could put this here. I believe there was like an extension to do live updates, right? Am I right? Let's see, live server, I think. There you go, live server. Or live preview? Yeah, live server probably. And let's try that out. Nice thing about this setup, it's so lean. You don't need any TypeScript toolchain. You don't need any of that bull crap. You don't need an MSVC compiler. You just need a freaking browser, VS Code, or even just Notepad or something, and you're good to go. This is what I really like about this kind of setup. All right, so we could, I guess, go live maybe. Allow, and server is start a port farmer dash, right? Okay, and we just get this. Can we just open up this here? No? I guess so. Let's try something. There you go, it works. It works. Okay, so I could just like literally just do all my VS Code. All right, sick. All right, let's see. So let's open up the WebGPU tutorial that the AI made. So a complete detailed tutorial for building a voxel render in vanilla JavaScript plus WebGPU, no npm, no TypeScript, no build tools, just browser plus local server. All right, let's see. So we're gonna go prerequisites, and I basically told it to make me milestones where from black screen to a live screen to a triangle to a full screen triangle and so on. Now the prerequisites, just a local HTTP server in JavaScript. So black screen to live, get a WebGPU context and clear the screen to a color. This proves your setup works. What you need, an adapter, a device, and a canvas context. All right, so first of all, I think I need probably like a script here somewhere. I guess maybe we could put it here, for example. Let's see. So first of all, can you just disable this autocomplete, please? It's so annoying. Let's go and let's just see what we got here. So you just create a script, okay? And you just create your code there. All right, so we got an async function main and the parameters, in this case no parameters. And now we just say if not navigator dot GPU, okay, then we got a little problem here. I guess we could just throw a new error. WebGPU not supported. All right, sick. And next we can grab an adapter. So an adapter, you just await. So basically it's async, meaning it's not necessarily that the renderer is ready the moment you call it. It could take some time, so you gotta await it essentially here. It's a future, I think. So here, request adapter, you can give it some options, or you could just give it none. All right. And so if not the adapter, then we're just gonna throw a new error. No GPU. Wait, they actually use no GPU adapter found. Okay. And do I actually need the semicolons though? I think maybe I do. And they just use like one quotes like this, one character quotes like that. All right, 6. So we got the const device. Wait, does JavaScript needs these guys? Maybe they do. I don't know, because like the autocomplete is not really helping there for some reason. So fine. All right, next up we gotta get the device. Await adapter dot request device. And here you could give it some descriptor, apparently. Interesting. Next up, you can grab the canvas from the document. So documents get elements by ID. And in this case, I just called it C. Let's call it canvas. Why not? Instead of C. Right? And I guess you gotta make a canvas, obviously. So let's create a canvas really quickly here. Canvas ID is equal to canvas. And the style, for whichever reason, is equal to width. And you just say 100 VW. I'm not sure what this VW means. And VH. I gotta look that up soon. But anyways, for now, this is fine, I guess. I don't actually need the closing thing, which is interesting. Wait. Do I have to maybe do something? Oops. Isn't it like this? Yeah, I think so. Maybe the AI just missed that. I don't know. Anyways, next. Oh, there is actually a closing tag there. Never mind. Sorry. Sorry. Okay, cool. Next step, what we do. So we got the script, and yeah, all right. So let's just create this stuff. Let's continue. So now that we got the canvas from the document, we could create a context out of it. So the context is equal to canvas get context. Whoops. Wait. Get okay, and here you could say 2D or whatever. And even there's options apparently, which is interesting. And so here we can just say WebGPU. to get a WebGPU context. Instead, you could also say 2D to just get like a 2D canvas context, or you could say WebGL here. In our case, it's WebGPU, which is the newest standard of rendering. Next up, we got a format. Okay, so navigator dot GPU dot get preferred canvas format. All right. Next. And I already forgot the semicolon here. I'm not sure if semicolons are required in JavaScript. I think there probably are, but yeah. Context configure. And here, wait, what? It says audio decoder, bro. Anyways, so the autocomplete in JavaScript is not the best compared to something like TypeScript, I think, maybe. But yeah, I haven't tried TypeScript though. But anyways, so device format, configure device format. So you just give it the device and then the format. And finally, we could create an encoder. So device create command encoder. Okay, cool. And then, so that's just for the command buffer. And finally, we create like a pass. So begin render pass. Begin render pass. And we got color attachments. Okay. And you got the view, which is our context get current texture dot create view. Okay, so that's how you do it. Next up, you got the clear value, and here you set the clear value. So let's say, let's just go with that. Fine. So B is 0.2 and A, wait, A is 1. Okay. That's the clear value. Next up is load OP. So they don't use enums here, they just use strings. And honestly, strings are OP. Store OP. Store. And all right. Okay, pass.end. And finally, device queue submit. All right, encoder.finish. All right, so that's that. Now let's see the page. Did I wait? What? Let's try an actual browser then. Let's see the div, like the console. Huh? What in the world? Canvas. All right, let's just open up Gemini really quickly here. Might have missed something. So let's see. Why this doesn't show anything? Oh my god, okay. I didn't call the main function. Where is that? Okay, hold on, let's call it. My bad. So after you like you make the main function here, obviously you call it. All right. There we go. Okay, cool, lovely. So we got the something clear into the window. Pray for OG Gear. Welcome to live stream. All right, so what we're gonna do next? Let's see. I'd love to honestly remove these borders. So let's ask it to how to remove the borders around the canvas. Also, what does that VW in the CSS means? Alright, so how to remove the borders? Add the simple style block into your head section. So you just say star margin 0, padding 0. So star basically every element, I guess. and box size in border box. And the body overflow hidden prevents scroll bars from appearing. And the canvas display block prevents tiny inline gaps below the canvas. What these fixes do? Display block. By default, canvas is an inline element like text. Inline elements leave a tiny 3-4 pixels gap underneath them for text ascenders. And overflow hidden hides any accidental scroll bars. Viewport width. Okay, percentages. I see. Lovely. I see. 1% the total window width and 1% the total window width. Alright, cool. Makes sense. Alright, so let's see what we got here. And honestly, let's just open up that thing in the browser itself, fine. And maybe we could even open the MD file in the browser actually. Can we? I'm not sure if we can. I mean, we could try, I guess. Hold on, desktop, website, and let's try opening up in the browser. I can't. I don't think I can. Yeah, no, I can't probably. Anyways, fine. Never mind. So, all right, how are we gonna do this? So confused right now. And let's just, I guess, pin this tab or whichever. So I forgot what I wanted. Damn it. Let's see. Yeah, I don't know why I did that. Fine, let's just go back here and let's grab that. Yeah, you could basically just do this and just do this and put this thing here, I think. And yeah. Oh yeah, I wanted to copy the I see why. All right, so let's go back to here and let's go. All right, so basically style. So in the body or where? I think in the body probably. Let's see. So style. And dash by Robtrap 1 stars 3. What the heck? Hello, Comport Box MPG. Welcome to the live stream. All right. So for every element, what we do is we remove the margin. So margin 0. Okay, that removed the margin. And next step, we make sure that the padding is 0. And finally, the box sizing is either border box, content box, inherit initial, or whichever. Border box apparently. Okay, I'm not sure what does that mean, but fine. Next step, we got goes into head, not body. All right, Mucho, welcome to live stream. All right, so we got a body and then overflow hidden to remove the, okay, to remove these. And then we still have this little gap there, apparently. I don't think it matters where you put the style, but I guess probably the idiomatic way is probably putting it in the head, but yeah. Next up, we got the canvas. Wait, canvas? Display block. All right, and that gap have gone. All right, sick. All right, so what is that? So this is the one that I don't understand. These other ones, I kind of get it. Explain more. And display block. I know there's also flexbox and stuff, but yeah, let's see. Because they override default browser behaviors that often cause unwanted gaps, scroll bars, or sizing bugs. To understand borrow the box, you first need to look how CSS calculates the size of an element by default. The default content box. The problem by default when you give an element a width of 200 pixels, CSS applies that width only to the inside content. Okay, if then add 20 pixels of padding and a 5 pixel border, CSS add those on top of your width. Oh, why does cause this box? If you set a canvas or container to the width and accidentally add a 10 pixels padding browser or border, its actually rendered size becomes... Ah, I see. So like those becomes inside of that block that you set the size of, not outside. Sorry, I mean outside, but if you want to override it, you gotta, I guess, use box sizing border box. Okay. The fixed border box, when you apply, you tell the browser width I give you is the final total width inclusive of padding border. All right, gotcha. Gotcha. Understandable. So border box, box sizing, and content box, display block. So why inline elements cause a mysterious gap are designed to sit inside lines of text like standard prose because letters with lower tails extend below. When your canvas is set to display inline, it sets on visible baseline. The browser adds a tiny 4 pixels white space gap underneath it. The extra pushes the page height to. Gotcha. Next up, change the canvas from text-like behavior to block-like behavior. Gotcha. Eliminate the bottom gap. Takes up its own line. All right, gotcha. I understand completely what the heck is going on there now. All right. Let's go back into business here. So this is understandable. Though I'd like one thing though, since we have like a very static canvas that nothing changes every frame, what we could do, let me look for the WebGPU samples. And I'm kind of excited about this. Now, the thing is about the newer graphics APIs is that they allow you to make your state or to compile your state at the start of the frame and never touch it again, which is very, very useful for slow languages like JavaScript. Because like what is slow is JavaScript, not the GPU, right? But here I recommended the GPU. So if you use something like the render bundle, where's the render? There you go. The render bundles here, which are the newer kind of like features of WebGPU, where instead of like every single frame, well, in fact, here we're not doing this thing anyways in every frame. I'm not sure why, interestingly. But anyways, so instead of like having to call this begin render pass and so on, which is very slow JavaScript code every single frame, what you do is you choose simply create an, oh crap, there's a lot going on here, interestingly. All right, let's see. Where's the, oh crap. This sample is way bigger. All right, so let's just see with the part where they create the bundle. Where's the render bundle? Pass encoder. Okay, render scene. Wait. Oh, this is TypeScript. I see. All right. So here, there you go. You create a render bundle encoder, and then you give it some color formats. You know what? Let's start. Let's see the clear screen here and compare it to the way the AI did it, and let's see if it actually made a good job or not. All right. Let's see. All right. So the canvas query selector. Okay, what's the difference between query selector and get elements by? I think probably the query selector you could maybe like put some more advanced stuff. And obviously there's the as probably for TypeScript. And then there's also this kind of things, navigator.gpu. So it would basically crash if GPU doesn't exist. Okay, and then you could even set the feature level. Await adapter request device. Quit if WebGPU not available or missing features. Ooh, okay, next. It got the device pixel ratio. I see. You know what? Let's just continue with the AI tutorial for now. We'll revisit that stuff later, I guess. Fine. All right, so we're done with that one. Now let's create a hello triangle, which is way more complex. So draw a single color triangle. This introduce shaders and pipelines. That runs in the GPU, runs once per vertex, outputs position. Okay. And this is the shader. All right, in the pipeline. So you create a pipeline. Obviously, I think you create it right after you create your context canvas. I mean, after you configure your context, right, or whichever, before your encoder, because that one would go into your frame by frame things. All right, let's create a shader module here. Create shader module. And the descriptor here is like code. And you give it the shader WGSL. Though I think you basically have to say shader WGSL here is equal to. I'm not sure how do you do like multiple lines in JavaScript, but like I guess you're supposed to do something like this. Let's. How about this? Does this work? No, I don't know how to do multi-line strings. Does it like mention that here? No, it doesn't. Okay, cool. Let's check that out. How to do a multi-line. I mean, I could probably maybe even find the WebGPU. I mean, here they're just doing import, which is actually quite nice. And I wonder if it would actually work out for me. But still, I'd rather just leave it as inline, to be honest. So, how to do multi-line strings in JavaScript. Oh yeah, backticks. Okay, sure. And I guess that's it, hopefully. Or we could just do this, I guess. I don't know. Maybe I have to do it like that. And next step, all right, we got create render pipeline. Fine. So like const pipeline is equal to create render pipeline. There's even a render pipeline async though, which is interesting. So you could compile shaders asynchronously instead of blocking the browser until they're compiled, but yeah. So layout auto, and the vertex is a, I don't know, object or whatever, or like a table, I don't know what they call it here. Module, shader module, and then you give it the entry point, which is obviously vertex main. So vertex main. All right, and next up we get the fragments, which you give it the same shader module because the code lives there too for both of the stages. And then you change just the entry point from vertex main to fragment main. All right, and targets format. Right, matches the canvas format. Okay, cool. Wait, format. There you go. All right, cool. Next, you got the primitive, and topology is a triangle list because there's other kinds of topologies like you know, line lists, points, etc. And even like triangle fans or whichever. But anyways, so the render pass add to the existing encoder. So now we have begin render pass, and then we set the pipeline before that and that. We say pass, set pipeline, obviously, pipeline. And then we draw 3 vertices, and the other ones are optional. And finally pass the end. Whoops, we already have pass.end, so there. So fine. Okay, and there we go. We got our first triangle WebGPU JavaScript. And like you could change whichever you want here. I don't know, like red, then just save, boom. You get like the, oh my god, just that alone is such a treat. Like to just save your code and boom, you see the change instantly instead of having to wait for the compiler. But anyways, so why it kind of, all right, I think the shader is probably nothing fancy there. So you just got like a vertex main function for the vertex entry point and a fragment function, and they're basically realized by this kind of decorator. So this kind of like sets the entry point for the vertex, and this sets the entry point function for the fragment, and we just have a built-in vertex index, and we gives out a built-in position vec4f, and then we just have an array of 3 vertices built in here without a buffer, and we just return a new vec4f with that position indexed using the vertex index. Nothing fancy there. And finally, the fragment, we just set a, you know, like a solid color. I mean, I could change this and just save, hopefully, and it would just work. Boom. All right, so it's a red triangle now. All right, cool. Now let's see what's next. So that's your hello triangle. So vertex main runs 3 times. Once obviously each call returns eclipse space position. All right, next up is the full screen triangle. So this is just a little trick that if you want like to fill out the whole screen with that thing, what you do, instead of having 2 triangles, which is a bit wasteful, you could just use 1 triangle and do it. So basically here, instead of having minus 0.5, like basically 0.5 in general, and honestly, yeah, so what you do instead, you kind of scale that up. Yeah, you make it 4x larger, 4 times larger than the screen, but only the portion inside the viewport is rendered. This is faster than a quad because 3 versus than 4, blah, blah, blah. Anyways. So what we're going to change here. So the first one would be, I'm not sure why I changed the winding order though. Yeah, I'm not sure why I did that. Wait, no, there's no winding order here. It's just the way it is. Okay, fine. All right, so you just do -1 and then -1. 0.0, and next up you got like here 3.0 and -1 here, and then you got -1 3, and there you go. And just the formatting bit, I guess, but yeah. All right, that works, I guess. And you got right now a full screen triangle. So that's sick. All right, it keeps on like resetting when I change this, which sucks, man. All right, anyways, so where do we go next here? A smooth gradient from bottom left dark to top right bright. And for that, you just get a UV. Wait, so you just grab a UV here. Yeah, this inline thing is kind of suck a bit, honestly, but yeah. So you get the frag chord XY, and then you divide it by basically the resolution. I see, so 800, 600. And then you could basically just use uv.x for the red, so you would get like a red gradient depending on like the x axis, and a vertical one in the green color part. And for blue we just have 0.3, and yeah. Now if I do this, whoops, I have no, can I have developer tools here by any chance? Console, is invalid due to previous error. In result value frag chord. Is it frag chords maybe? I think it might be frag chords or something. Wait, what? It is called frag chord.xy. Maybe there's just a typo in the code there. I mean, if I just copy this code just like that. Ooh, what the hell? So what was wrong here? I don't get it. Frag chord xy. Oh, I see. So like in the fragment main, you gotta obviously pass in this built-in position frag chord. I was like, what? All right, so built-in position frag chord is a vec4f. All right, and now we have the same kind of result. So a gradient along the x in the red and the y in the green. All right, lovely. Next, so we're gonna go next to the textured quad, I think. All right, so draw a rectangle with a texture. This introduces vertex buffers. So vertex buffer, GPU memory holding per vertex data, a texture, sampler, and a bind group. So here we got the vertex data. Each vertex position plus text chord is equal to 8 floats. And put here ignore. And here you just got like the X, Y, and UV. So let's just copy this part. And I don't know, let's do it maybe after the pipeline and before the encoder. Fine. And now we got that array. So right now, instead of like hard coding the vertices in the shader, right now we're just gonna use some buffer for them. Okay, so the shader is this. So now instead of basically using the built-in vertex index to like index into the array, instead we're just gonna use an input variable, which is a struct called vertex input. So we kind of like, so basically there's two ways you could do this. You could either just put in here like location 0, like this, and then like this, right? Or you could just create a struct like this, and just put it. And then you could just right now say input vertex position, which is way cleaner, at least in the arguments. And there you go. And finally, instead of built-in position vec4f like this, you could make a struct for that too. And the built-in position goes here, which we were already using here, but here you could even named it instead of just vec4f. But yeah, next up you got like the UV, which is from location 0 in the vertex attribute. And yeah. And that's it. Now obviously we just make sure to set the vertex output here. And finally, we create a new vertex output struct and we set its fields. We set the position to the input.pos. So here, since we don't want to do any kind of vertex transformation, we just forward the position as it is to the fragment shader through this vertex output struct. And same thing with the UV. Though, except for one thing here, instead of just forwarding the vec2 that we got from the vertex buffer, we just make it a vec4 instead. With 0 as the z-axis and 1 as a w-axis, and we just forward it into the fragment shader. And yeah, that's basically that. So we could just pretty much just copy this, and let's go to vertex main, And that's your vertex main. Next up, you got the fragment main. Now, obviously, instead of this, we just, the other nice thing about this is that since we use structs, we can make sure that we're using the same struct both in the fragment and the, so we don't have to like change here and change here. We could just change the vertex output struct and it applies to both, which is lovely. Makes less for bugs. And next up, we, instead of now just returning color, we return texture sample. Since we're gonna have like a texture, we're gonna use this function called texture sample. You give it apparently the texture and a sampler, and then you give it the UV, like which position in the texture you want to sample. And what it does basically, it goes ahead into the XY position that you gave it through the UV here, and tells you which color is in that position. And then you basically just return it from the fragment shader. All right, finally, now we're gonna change the pipeline a bit apparently. So vertex, so we add this buffer. Since we're gonna have some buffers, instead of just hard coding the array of vertices in the shader, we're gonna need to insert this buffers layout thing. So we pass it in the vertex object here. We say buffers, and it's basically an array of these objects. So you got like the array stride, which is 16, because there will be like 4 floats times 4 bytes. Oh yeah, because like a float is 4 bytes, so yeah, gotcha. Or honestly, instead of 16, you could just do it, you know, 4 times 4, but yeah. Next up, we got like the attributes. So for the attributes, we got 2 attributes. The first one would be shader location 0 with offset 0, and its format would be float 32x2. Now it sucks that we don't have like enums and what is it called? Enums like here, but yeah, whatever. All right, and then you add another element into the attributes for the second vertex attribute, I guess. Yeah, shader and autocomplete, obviously. But yeah, shader location 1, and then offset is 8. Oh, it auto, like, I see. So it kind of infers the size for you. Just tell it the format. Interesting. Okay. So the format is a float 32x2. Okay. So that's, so the first one is for the position. It's in shader location 0. And the second one is for the UV attribute, which is in position 1 with an offset of 8. Offset of 8 because 32, this format takes up like 8 bytes, essentially, I think. Next up, what we got? Yeah, that's pretty much it. You just add this buffers thing. Next, creating a texture from a canvas. Ooh. Ooh, ooh, ooh. Ooh, off-screen canvas. Interesting. Interesting. Okay, so where the hell do we even create that? Let's see. I guess let's go outside of this function main here. It's becoming huge at this point. And we're going to create a new function called create checker texture. And it takes in a device and a size, which by default could be 64. Okay. And here, apparently, we get a canvas. So here we create an off-screen canvas. So basically an off-screen render target. And then you give it the size in the width and height, essentially. Okay, next up, you got the context. So you get, oh, okay. I see what they did here. Interesting. So like you could use the 2D canvas context of the browser to create a texture. I see. And then just like blit that into your main WebGPU render. That's awesome, man. Oh my God, that's so useful. This is another thing nice about like the browser is that you have all these cool things. Like even if you want, let's say, to decode and encode videos, you don't have to add any libraries or whichever. Like you could just use the browser stuff. You don't have to constantly keep on adding libraries here and there. Like just the browser alone have everything you'll ever need most of the time. So yeah. Now you could use Three.js actually to do something similar to the rendering here, but Three.js is huge code. So yeah, I mean, if you're just gonna do like, let's say PBR or whichever, something standard like that, then it might still be worth it to use Three.js because it's pretty like optimized for that kind of advanced case. But if you're just wanting to do a triangle or whichever, it's just too heavy. But you could still use it anyways. But yeah, I'd rather just go with no dependencies for now, so I could learn more. But anyways, so here we got the cell size, which is like 8, okay. And now we have like a for loop. Okay, for y is equal to 0, y is less than the size. All right, so here we just kind of like have a 3D for loop, so we could, not 3D, I mean 2D for loop, so we could fill up that texture pixel by pixel, or like row by row and column by column, essentially. So that's the for loop for the y, and here the for loop for the x. So we say x plus plus. And now we say is white. Okay, so is the checker box, is this particular pixel in this particular x and y coordinate, is it white or black so we can create the checker box? So this is kind of like a shader, like a fragment shader, but in the CPU. I mean, we could a cool little thing we could do maybe is to use actually compute shader later on to generate this, for example, just as a little exercise. But anyways, so here we got the x greater than, like, divided by cell size or 0. Is that or? Interesting. All right, so x divided by cell size or 0. I'm not sure what that or is for, but let's see. Plus y divided by cell size or 0. And then you basically take that whole thing and then modulo 2. And you do this 3 equals 0. So if it's basically equals to 0, then it's going to be white. And finally, we say fill style here is equal to is white. So if it's white, then we're going to use the 3 Fs. Otherwise, we're going to use this 3 8s here. All right, and we're good. Next, we got the fill rect. Okay, xy 1 1. And you're done. So this is, I guess, a bit terribly inefficient because like you're making a rect for every single pixel. Yeah, actually, why not just fill rect per cell size? I don't know. I don't know why I did it that way, but we'll have to ask it later on. Next up, let's see. Finally, we can create right now a texture. Wait. Okay, cool. So device create texture. And you just give it this kind of object or table, whichever you want to call it in JavaScript. All right, and then you got the size here and the format. RGB AHU norm. Whoops, what the hell? And then the usage. So GPU texture usage. Wait. Okay, and then you use texture binding usage because we're going to be using it as a texture to a shader. And finally, you gotta make sure to also add GPU texture usage.copy DST, because we're gonna be copying some data to that VRAM texture thing, you know. So next up, we upload that canvas to the texture. So how you do it is you create an image bitmap, and you do that by simply doing await create image bitmap apparently. And this takes a image bitmap source and some options. And in this case, the source is canvas. Okay. And then what we do is we say device queue. Oh, you don't have like in WebGPU. Apparently you don't have different like handles, like separate handles for queue and device. You just say device.queue. All right, interesting. Very handy instead of having to create a structure ourselves and bundle them. But anyway, so copy external image to texture. Okay, so you don't have to create a staging buffer or anything. Okay, interesting. Next up, you could basically set a few things here. So first of all, the source, which is an image bitmap. And next up, you got the texture and that you're gonna upload this data to, and then finally the width and height. This is pretty cool. Very simple to do things. Lovely. Love the simplicity, man. Nice. Like compared to native APIs for WebGPU, this is a freaking like amazing. Await expressions. Okay, so this gotta be, I guess, an async function. Yeah, I pretty much missed that one. But anyways, next up, what we could do is you return that texture. All right, cool, lovely. And that's basically that. And that's how you create a checker texture using a 2D canvas into an off-screen canvas. That's pretty sick. And then you basically just like, you fill out the data, you generate the data using the context and the canvas. You create a GPU texture of type RGB AU norm. And obviously you set the right usage flags. And then finally you create an image bitmap from the canvas. So you could convert that canvas into pixels that you could upload then to the texture in VRAM in the GPU using this copy to external image to texture through the queue. And that's that. It's really that simple. Lovely. Doing this like in low-level code is much more complex than that. Anyways, next step, what we got? So, okay, so we got the set pipeline. Where is that? Okay, so we got set pipeline. We got like draw. Now instead of 3, we got like a quad, I think. Yeah, 2 triangles. So obviously 6 vertices. And then right now we could set the vertex buffer that we're gonna use. And it's, wait, it didn't tell us how to create a vertex buffer, did it? I don't think so. Wait, do you just pass in an array directly? Quad vertices. Wait, I don't think, but no, yeah, it didn't tell us how to do that. Well, we could check the examples. We could check the other samples. All right, fine. Anyways, you set vertex buffer. You set it to vertex buffer because like you could have multiple vertices, vertex buffers essentially. So like in our case, we have one vertex buffer that contains all the attributes. In our case, we only have currently 2 attributes, the XY position and the UV for the texture position. But if you want, instead of like interleaving them in one buffer, you could, for example, create 2 buffers. You could create like a vertex pause buffer, then, you know, say vertex buffer and then say 1, and just have a vertex UV buffer if you don't want them interleaved. But yeah, but in our case, we're just gonna have them interleaved, which is fine. All right, so how are we gonna do this? Okay, so what's next? Set the vertex buffer and you draw. And you also gotta make sure to set the bind group though. All right. Are you still on CachyOS? No, I'm not on CachyOS. I'm on Windows. I'm getting older. I'm too old for messing with the Bluetooth and like Wi-Fi just to get my headset like working. And I constantly hit bugs with the NVIDIA. I mean, it definitely kind of improved a lot recently. You know, it was not bad, but still, for example, the issues that I still had with NVIDIA on CachyOS on Linux was, for example, when the computer kind of like goes to sleep, what happens is when I, turn it on again, it just like gets the whole screen gets dimmer for whichever reason, and I can't take it back unless if I restart. That's one thing, for example. Second thing is the Wi-Fi is so slow for whichever reason. I mean, before I was just using, because I was on another home, on another house, I was using LAN cable, so I didn't notice the issue. But now I'm on another house and I'm just using Wi-Fi, and so I had a lot of issues with Wi-Fi. I mean, one thing I had fixed is MTU. Like, I made sure that the MTU matched my router, my fiber router, which, like, instead of 1500, which is perfect for LAN, for cable, instead I set it to 1492, which was kind of better for avoiding packet fragmentation. And so it was a little bit better, but still, from time to time, there was some issues like with Wi-Fi, it either slows down or whatever. And also another issue I had with Linux, CachyOS, is the Bluetooth headset. Sometimes it works, sometimes it doesn't. Uh, so it kind of sucks. So honestly, I just gone back to Windows and I'm much happier right now, to be honest. So yeah. Another thing obviously is have easily like being able to, let's say, run whatever you want. Like LM Studio is so handy than just using the command line using Olama for the AI. Another thing is also, what is it? Yeah, for example, if I wanted, like, for example, sometimes I use the agent, the AI agent, and I want to control my computer and like monitor it through my phone. So what I like to use Parsec. I'm not aware of like something similar in, I mean, there's obviously probably some software in Linux too for that, but Parsec, I found it very cool. It's pretty lovely. What else? Also, obviously, if you want to install Minecraft or Roblox or whichever, then you just gotta use Windows. I mean, obviously you could, but yeah, it just requires a lot of maintenance, and I'm honestly getting too old for that crap. So I just gone back to Windows at this point, and I'm much happier. Anyways, obviously there is some things that I've missed about Linux, like its speed, for example, for compilation, but I'm not writing Rust, at least for now, so it's great, it's fine. The other thing also is the browser. So WebGPU support, which is like a very newish API. So the support there is still lagging compared to Windows. But yeah, fun fact, I installed Windows on my desktop and the Bluetooth audio started stuttering every 0.5 seconds. Some Linux works fine, but I also run with Wi-Fi driver issues here. Yeah, it just sucks. Like, honestly, there's not a silver bullet OS. Each, like Linux, both Linux and Windows have their own issues and their own perks. But honestly, at this point, I'm just stuck with Windows, to be honest. I like Moonlight plus Sunshine. Yeah, I heard of Sunshine, honestly. I heard of Sunshine for Linux. I tried, I don't know what issue I've hit with it, to be honest. Because, like, the AI have recommended it for me, and I tried installing it, but I don't know what happened after. I don't remember. I hit an issue which I couldn't get, or I was just too lazy. I don't know. Alright. Yeah, open source. All right, so let's continue. We got the set pipeline. Next up, we got the bind group. Honestly, I really love this so far. And what I'm really like excited about when it comes to using the web browser and JavaScript instead of like native WebGPU is the fact that I could easily, as you've seen here, I've easily can use like the 2D context without adding any kind of libraries or whatever. Um, which is pretty sick, especially like let's say for UI or whatever, and just generally like procedurally generating textures, etc. The other thing that I'm really excited about trying in the web browser is you can actually, without any libraries, upload like basically decode video frames, and then you could basically render them using WebGPU in the browser. And so you don't have to like fight FFmpeg or fight any kind of library. It just works. No libraries, no nothing. It's just like the browser stack, which is honestly amazing. And like if you want to make, let's say, capture your screen, even like you want to create a capture thing, you could probably make it work too, just using vanilla browser, I believe. Same thing if you want to make, for example, let's say you want to stream frames like through the network, you could probably use WebRTC support, hopefully, maybe in the browser. So I'm very excited about these because like trying those in native code like Rust or C or C++ or whichever is such a freaking pain just to get it to build, first of all. So JavaScript is so good, man. Next, will you ever try Odin on stream? I don't know. I just don't see anything interesting on Odin that I have to try on. Like compared to, let's say, Zig, Rust, or C or C++. But like if there is demand for it, if there's a lot of demand for it, I probably would maybe make a pull. Honestly, I'd rather stay away from low-level code at this point because I'm just so burnt out of it. So that's why I'm coding JavaScript. Just getting away from low level because oh my god, what the hell is that? Because like you feel like you're going through a swamp trying to make anything work. You just have to constantly deal with libraries, deal with all sorts of crap. But here in the browser, what's nice is you don't have to worry about windows or libraries or glue code or whatever. It just works. And you don't have to like fight with the types either, and so on. Yeah, Skylight NRG, welcome to the live stream. It's insane what we have in browser now. For example, WebCodecs API with hardware encoders. Yeah, exactly, decoders. It can be used for encode video frames on the fly from Canvas. Yeah, so this is what I'm really excited about in JavaScript, coming from native stuff, because I could do all these sorts of cool things without using any kind of libraries for window. Like in native, you have to use a library for windowing, a library for WebGPU, and you have to wait for it to freaking compile. WebRTC, if you want that, just forget it. Because like setting up WebRTC, you need like the Google library, the Chromium library for that. If you want some great support, I mean, there's probably some lightweight alternatives, but they're not like complete. They don't have complete support. But yeah, either way, you just get a freaking mature runtime like everywhere on every single device, and like you get all devices for free. And there's even the webcam here, crazy. And there's even like some newer APIs like the file API and so on, which you might not even need Node.js for that at this point. But you got the point. So I'm very excited about these things. And in fact, when I was actually trying to make like a video editor and a video recorder natively using C++ and C, and I've kind of like noticed one thing that kind of waked me up to the web platform is, yeah, here. So in Microsoft Windows comes with Clipchamp, right? And Clipchamp, I believe, is probably made in React. So just JavaScript or like TypeScript code. But yeah, effectively it's just like JavaScript code when it comes to the actual runtime, and yeah, this is just WebStack, bro. And you can create like a freaking video and it's just kind of fine. It's not that bad. I mean, it's a bit slower, obviously. And obviously, if you want to do something very, very advanced, it kind of suck. Though I believe it could probably be optimized with things like, WebGPU now that we have and all these kind of APIs. But I believe this Clipchamp is just like a little like React app pretty much. But yeah, it's just great. You just can record stuff like... you could record your screen and all sorts of things, and you can edit and everything, and it's just the web stack, not native. And I was very surprised to see that it kind of works. I mean, it's not the best performance in the world, but it works. So yeah, and that's when I started to kind of consider the web stack to be a bit of a serious platform that you could actually create some cool tools using it. But yeah. So then, what do you think about WASM? I mean, WASM is nice too. It's lovely, but still, you don't get as much like compiling to WASM takes too much time. But here, I could just like try changing anything, and then I see the change directly, and I don't have to fight with libraries to get WASM support and like tool chains. I could just write freaking JavaScript. The other thing is also startup time, So like WASM binaries are usually quite huge, right? So it takes much longer time to kind of like upload them into a website. So by then your user have already have already quit before your WASM binary have downloaded. On the other hand, JavaScript, it's pretty quick. You just upload the JavaScript, you minify it, etc. And that's actually what bundlers like Vite and so on. I feel like they're over engineered, but they're doing some few things. Like they're basically minifying your JavaScript, making it as small as possible so it can be uploaded much faster. And they're doing some other tasks, like I believe maybe also tree shaking, so they could remove things that you're not using, like some function. Like if you're using libraries, and let's say you use 3.js, it would try to include only the functions that you're using from 3.js, for example. But here, I'm fine. I just use like regular, great old JavaScript code. No minification, no toolchain, no nothing. But yeah, honestly, very, very excited about this kind of JavaScript stack, to be honest. But we'll see. Okay, so where we were. Yeah, we were working on that textured quad. All right. Draw a rectangle with the texture, blah, blah. All right, so did we put, yeah, we put the quad vertices, so we gotta realize how we could create a vector vertex buffer, and the AI missed to tell me how to do that. So let's look for that. Let's say, for example, hello triangle. Do they use vertex buffers here or no? Not really. Okay, not. All right, let's check out vertex or rotating cube. Does this use a vertex buffer? Yes, it does use a create buffer. Okay, cool. But this one, it's actually using mapped at creation. Vertex buffer get mapped range. Is it? I think it maybe it's using rebar or something for this one. Interesting. Okay, so let's just copy that code. So after my quad vertices here, what I'm gonna do is I'm gonna say vertices buffer or vertex buffer is equal to device create buffer, and let's go. But yeah, generally I'm very burnt out, to be honest, of like fighting with my toolchain, with my language and libraries and so on. So JavaScript is like the most sane way to code without libraries or anything. Like just the browser APIs alone are very powerful to do almost everything. So yeah, it's pretty much lovely. Also, like typed languages, while I kind of miss the autocomplete and so on, but to be honest, and like the kind of robustness, safety, quote unquote. But honestly, I feel like I just kind of got recruited into kind of like a cult of type safety and memory safety and so on. But honestly, like dynamic code is kind of fine. Hopefully I wouldn't regret saying this like in the future when I actually maintain a production dynamic code thing. But yeah, but generally or currently I'm only doing this as a hobby, so it doesn't even matter for me, at least for now. So yeah, it's pretty cool. All right, so anyways, next up, so we got the vertex buffer and you just tell it your byte length. Wait, where is that coming from? Cube vertex array. Okay, where the hell is this cube vertex array coming from? That's weird. Cube vertex array. I don't understand where the array is coming from. That's weird. Uniform buffer. Okay, how they're dealing with this vertex buffer, sorry, the uniform buffer, for example. Oh, they're just hard coding the size there, okay. And they're using like a library called matrix or whichever, which we could use later on, but not now. And here we got transformation matrix by offset by length. Oh, that's strange. But you know what we could do? We could just go ahead and research about float32 array JavaScript and go to the source. And let's see what kind of stuff they have. Prototype bytes per element. Ooh, okay. You can actually get the length and then you can get bytes per element. Is there a direct way to just get the whole size in bytes, or do I just have to multiply those? I mean, from what I've seen so far... Wait, what the hell? Oh, byte offset. What? Why a byte offset? This is interesting. Okay, you know what? I think I'll let the AI give me some context here. I'm coming from low-level languages like Rust, C++, etc. Can you give me some context about the array types that exist in vanilla JS, like float32 array? So belongs to JavaScript's typed array family, which provides contiguous fixed-length row binary memory buffers just like a CD vector or heap allocates arrays in C and C++. In vanilla JS, array-like data structures split into two distinct words. You get the standard array, which is a dynamic heap allocated JavaScript objects. It doesn't basically care about the type. You could use whichever, I think. And then you got the typed arrays and the array buffer. Contiguous fixed size binary data blocks. Okay, so they're pretty efficient. Typed arrays, direct memory buffers. Under the hood, a typed array isn't actually storing data itself. It is a typed view over a flat contiguous block of raw memory called an array buffer. Oh. Okay, equivalent to void or box. I see, so you got like a tapped array. Wait, okay, so basically this float32 array is just like a wrapper over a buffer, an array buffer, essentially, which is like just a byte buffer, basically. All right. Clamped, what does that mean? Custom UH. There's even big ints, which is quite lovely. Note on commonly used in Canvas 2D pixel manipulation. Automatically clamps, ooh, instead of overflowing or wrapping. Nice. I don't know why you would use that instead of just like clamping yourself, honestly. But anyways, when writing WebGPU WebGL, so allocate a raw 16 byte buffer, new array buffer, so it's like malloc, and then you create a view over the buffer as 4 byte floats. All right, no new float32 array. Interesting. Though here I was just able to just give it the data directly. Okay. Alternatively, create directly. There you go. Allocates underline array buffer automatically. Gotcha. And then you could get the byte length and the length. So the byte length is 16 bytes. Oh, you could just use byte length. Okay. So here you could just say quad vertices dot byte length, I think. And there you go. All right. So, and then you got the length And then you also got that prototype element thing that we have seen in the documentation, like prototype bytes per element. You could also use that if you want to kind of like infer what kind of type this view is about. So this kind of float32 array, etc., compared to buffers, are just kind of like, you know, a slice in Rust or whichever, apparently, I think, from what I understand here. Manual Indonese and mixed access. If you need to parse structured binary packets with mixed types of specific Indonese, like a C struct, you use data view. Structured binary packets. So write int 16 at offset 0, little Indian equal to true. And write float32 at offset 2. Alright, that's interesting. And array buffer. So here you basically allocate memory. Here you just kind of like make a span or like a slice or whatever you want to call it, depending on which language you're coming from. And yeah, you just use the regular ways of doing things. And then here's standard array high-level dynamic list. So standard JavaScript arrays are not contiguous, low-level primitive arrays. They're dynamically resizable, obviously. Behaves like an SCT vector GS value or Vic enum value. Sparse and heterogeneous. Elements can be of mixed types and indices can have unallocated gaps. Unallocated gaps, okay. So it's kind of like a hash map to some degree. Alright, engine optimizations V8 will try to back standard arrays with packed C++ arrays under the hood if you keep them homogeneous. Alright, so this is a little optimization. If you don't do this kind of access, apparently you could try to optimize it for you. But it falls back to hash maps if abused. Alright. So key differences for C++ Rust developers. Fixed size. Once created, typed array's length cannot change. No push or pop. You must reallocate a new buffer to resize it. And the zero initialization. Allocating typed array automatically zero initialize memory. Okay. And no unsafe pointer arithmetic. You cannot access memory outside of buffer.byte length or construct arbitrary pointers. Bound checks are enforced by the JavaScript engine runtime. Alright, that's a pretty good primer for JavaScript arrays, and honestly it's quite lovely. It's much more powerful than I thought it would be. Alright, so I guess let's go back to business now. So we got the size out of the way there. What's next? Oh yeah, let's go back into that thing. Let's go back to the example really quickly because we have to kind of continue this thing here. So we have set the size. What's next? We need to set the usage here. So the usage is basically GPU buffer usage. Wait, is there like some sort of extension that would give me some better JavaScript like type stuff, etc.? I'm not sure. Babel JavaScript. So hold on, let me ask the AI. So I'm using VS Code to write vanilla JavaScript WebGPU code. Is there an extension that can improve the complete, like the autocomplete, or is it just what it is? You definitely don't have to live with poor autocompletion because WebGPU is relatively new, web standard. If VS Code's default JavaScript language doesn't always include the full. I don't want to deal with NPM right now. I don't want any kind of tool chain. But apparently you could just say npm install WebGPU types, then create your file name gsconfig. Well, I mean, it's save dev WebGPU types. If you're writing raw without node modules or packages, simply add this / directive at the very top of your JavaScript file. Ooh. Oh, right. What? Ain't no way. Let's see. Wait, does that work with hold on. Where's the JavaScript? Here, I guess. No? Wait, no. I mean here. Oh, actually here. Okay, can I just do this? Can I find definition file? Huh. Did they give me like a wrong link? No, it's right. And that basically gives you the types essentially. So it's right. I don't know what's up with that. Okay, where do we go? Okay, I was here. Essential VS Code extensions for WebGPU. Okay, so JavaScript, you don't have any particular extension apparently. You just use the native one in VS Code. And pro tip, oh, by the way, wait, hold on. What kind of extension have I installed so far? I see, all right. Yeah, I don't know. Let me ask you about this kind of little error here. Does it work inside of script check in an HTML file inline 2? Or does it have to be a separate JavaScript file? No, that does not work inside inline. TypeScript's language engine only scans JS and TS on your disk for triple flash. If you're building a pure without package JSON, create a JS config file. Oh, would that work? I wonder. I mean, alright, let's try it, I guess. I don't know. Hopefully it's not just hallucinating. But let's try. And let's just download this. Types this. And then what? Save it as WebGPU d.ts. Okay. And all right, let's just try it. It said that it wouldn't work here. It'd have to be like an external thing, but let's just try it out though. I mean, it didn't actually kind of complain here for whatever reason, which is interesting. But let's say device. Does it now have all the things? No, it only includes things that we already used. So I don't think it works. Yeah, I don't think that works. No, inline script works with VS Code. Okay, wait, does external GS files... I mean, actually, I am using a server anyways, so it should work actually, never mind. All right, so how can I split GS into its separate file? I'm confused by the module system. I heard that there is multiple. Here's a quick breakdown followed by the modern standard way in browser-based JavaScript is using ES modules. App.js. I kind of made sure to tell it that so it doesn't tell me like an older way of doing things. Because I heard bad things about that. But yeah, move your JavaScript into a file named app.js. Why not just script.js? That's a little bit better, I guess. And link it in HTML using type module. Okay. So you just do basically. So first of all, let me just copy over these things. Just like this, and we're gonna put it here. And now instead of this, we keep those tags like that, but we say type is equal to module, and then src is equal to app.js, or in our case it's script.js. Right. And just to test this out, what we could do is I'm just gonna maybe like comment out that main function. Then can I say console.log? Hey. And then what I could do next is come here and grab the developer tools. And there you go, I got hey. So it works. It works. All right, now the real question is right now, does this, ooh, okay, it seems like it's interesting. So does that mean it works? Let's find out. Let's find out. All right, so let's see something. For example, I guess device. Oh, okay. I think it works now. It works. Shit. That's cool. All right, for example, like the query thing and the compute pipeline thing, I didn't use it, and it still like gave me the autocomplete for it. And it even gives the documentation. All right, so that's lovely. Oh my god, that's way better, man. And you just do WebGPU d.ts like this. Sick, that works. So syntax const fs require and module exports, older Node.js backends. Script tags, no modules, old school browser. Okay, behavior puts everything into the global Windows scope, variables in file leak. Ah, gotcha. So this is what I remember from the old times. That's what I was using usually. But right now I just gotta add that module thing, module type thing. Okay. Using export and import. You can actually put a comment here. Weird, okay. Okay. Can I import WGSL files directly too? I'll review or snippet a few minor WebGPU runtime errors will present that would prevent it from drawing. I don't care right now. Okay, I'm gonna take a little break and I'll come back. Okay, I'm back. I'm back. All right. So yeah, let's continue what the heck we were doing here. So we were trying to break things up into multiple files. So we got basically this WebGPU types working without any kind of bundler or external tools other than just VS Code, which is nice. We basically just installed this WebGPU TS kind of thing. And we got types even in JavaScript. So basically we're using this TypeScript thing to get types in JavaScript. And obviously this TypeScript, you don't have to ship it with the JavaScript code. It's just there for the IDE essentially, which is pretty sick actually. Did I enable the mic? Yes, I did. Okay, cool. All right, now I gotta figure out how, if it's possible. So by default browser do not support native statements like import shader from. GSF, because JavaScript only know how to execute GS files. However, you can easily load and work with externally using either vanilla.js or build tool. Using fetch, okay. There's a whole lot of drama behind this fetch function. This simple little function that just makes an HTTP request, there was a whole lot of drama about it. I stumbled upon it like when I was researching about JavaScript stuff. Kind of was getting familiar with the ecosystem a bit. But yeah. Anyways, so you basically just create the shader. Node fetch Axios movement. Yeah. I wasn't aware of that. Like, it's just a separate world altogether. A whole war. Just because of one function. And like the whole history about like XHR and all sorts of cool things. But yeah. All right. And like promises. But anyway, so we got shader to be GSL, and what you do. So you just load the shader. Okay, gotcha. Use invite. Hell no, I'm not gonna use any tools for now. Unless if I'm really done. But invite pulls in file contents directly into a GS string the build time. Yeah, I got it. If you want syntax highlighting, you can also install using Webpack or rollup. If you're using Webpack, you can use the built-in asset source module type. For a quick, yeah, I could probably use fetch then, fine. Let's use fetch. So, sure. So we're gonna have like an async function, load shader. Also, I don't need this. So load shader, and then you get like a URL, and then you just do a response is equal to await fetch URL. And then if not response, okay. Yeah, particularly about this okay thing, because like format 4 is not an error. So that was one thing that I've noticed on that drama. But yeah, so failed to load shader from URL. And then we finally return the await response.text. And that's that. That's how I guess you do it. And now I could hopefully move this script into its own file. And we could call it shader wgsl. Just like that. And hopefully we could install some WGSL extension now. And let's see what WGSL analyzer, because I believe this one is not, yeah, like last released 2 years ago, but this one 3 hours ago. So let's install this one. And there you go. And now we got some cool types, which is lovely, way better. Oh my god. Okay, so what we're gonna do next is we're gonna load that thing. Okay, so honestly, I think I'm just gonna remove, well, I mean, I still need the MD file anyways. Anyway, never mind. So how are we gonna do this now? We're gonna go back to, I guess, what is it called? Yeah, also another thing we could do is we could grab this style and put it in a style sheet too. But anyway, let's start with the JavaScript code. Where is it? Script.js. And let's remove right now this part. And I believe I could right now just say await load shader. And then give it some URL, which, how do you do it? Okay, so you just do this dot slash shader dot wgsl, I guess. And now I guess that works. And can we just console.log loaded shader wgsl? Whoops, just like that. Let's see. So the developer tools, where is that? I just got a hey though. Oh, let me grab back my main function here. And let's see, so the developer tools. And there you go, it says loaded shader, and yeah, it works perfectly. Oh my god, let's go. Nice, nice, nice. So I could remove this hey now. And I could remove the, where's the other one that I put it? There we go. So let's just remove this console.log for now. And we're good to go. What's next? Fetch the raw text file directly and shoot the okay, cool. Use invite, blah, blah, blah. All right, so I think we're done with that part. Now let's just move the CSS too, because why not? So how do we do that? Well, I guess we just probably say style.css. And just like that. Shift tab, and we're good. Now I guess if I remember, I'm not sure if I remember how to do this. I guess rail sheet or something. Yeah, I don't. How do you include a CSS file in HTML? Link rel. Oh yeah, I forgot about that part. Link rel. So link rel is equal to style sheet, and then href, and then you give it the link, which in our case it's style.css. And that's that. And yeah, and we're done. Now I just can remove this thing from here. And we're done with the HTML file and the CSS file, and yeah. Now that's sick. Alright, so it tells the browser that the link file is a CSS style sheet, and href defines the file path. Cool. Alright, cool. Now we could go back, I guess, maybe to business or... Alright, so where we were... I think we were working on maybe the shader, I remember. Yeah, let's see. I guess let's go back to the MD file now, and we were in the textured quad. And yeah, okay, so texture sample, my texture and my sampler, as you can see, they're in defined here. So you gotta make sure to define them. So you do it this way. You use groups, group 0 and binding 0, and var my sampler. I mean, honestly, can I just call it sampler? Or is it like, yeah, could it be like maybe a built-in function or something? I don't think. Can I just do this? Wait. No, okay, so it's a built-in. That's why. My sampler. All right, fine. And then group 0 and binding 1. and var my texture is a texture 2D of type F32, because you could have multiple types of textures, obviously. Wait, did I actually edit format on save? Yes, I did, but apparently the WGSL, I guess, maybe doesn't support that. But anyways, all right. So I think that's that. Yeah. So we're good in the shader side, I guess. Next up, we got the pipeline. This one we already did it. This one we already did it. And then finally the bind group sampler plus texture. Okay, so just create a bind group now, I think. Okay. Does it err about that? Well, obviously this one should be the vertex buffer. We created the vertex buffer. Oh, actually, I don't think we have finished with the vertex buffer. Yeah, we definitely didn't. But now we have, lovely, we have autocomplete, which is lovely. Okay, so that was what we were working on, essentially. So let's go back, well, not here. Not here either. Yeah, here. So this is how you create apparently a buffer. You say dot vertex, and then if you want to basically use, I guess maybe rebar this is, or just like they're just using the staging buffer. I don't know which one exactly, but yeah. Anyways, or both. I don't know. Next up, so we map that at creation. We map that buffer at creation. Then what we do is we create a new float32 array. Vertices buffer get mapped range. Oh, I see. Now that I've read the documentation, I kind of understand what they're doing here. So what they're doing here is basically they're getting the mapped range, which I guess is probably just an array buffer or something like that. Is that true? Yeah, what this returns. Yeah, there you go. It returns an array buffer. And then you could give it the offset and the size if you'd like. Otherwise, I would guess it probably just gives you the whole thing. I think so. But either way. And then you basically kind of like wrap it in a typed array, which in this case is float32 array. All right. Get mapped range. Wait, can't I just open up this thing in here too? Hold on. How do you create like a new browser tab? Quick open browser tab or open integrated browser. Okay. Can I do this? All right, that's way freaking better. That's way freaking better, man. All right, so yeah. Okay, so how are we gonna do this? Let's see where we were. We were here, I think, or what? No, wait, I'll go back. Okay, we were here. All right, so new float32 array, get mapped range, and then we finally set it to the cube vertex array, which I'm not sure where they're getting that from, but I guess my quad vertices is probably what we want here, maybe. Yeah, because I don't know where. Oh, there is a cube TS here. Okay. So yeah, there you go. Cube float32 array. All right, cool. Gotcha. That's lovely. All right, so let's see. So we give it the quad vertices, and then we say in map once we're done. Well, vertex buffer, sorry. So in map, and you're good. So yeah, that's basically that. You just map it, you set the data, and then you in map it. sick. Now let's go back to our tutorial, I think. Are we missing anything so far? Textured quad. So we got that out of the way. Are we creating the bind group though now? The bind group. I think we still missing the bind group though. Where's the bind group? There you go. So set bind group 0, comma bind group. So I'm not using semicolons and it seems fine. Wait. Let me ask there really quickly. Do I have to use semicolons in modern JS? No, okay. All right, even better. But wait. Oh, well, hell no. Yeah, there's a big trap there if you don't use semicolons, apparently. Yeah, no, use semicolons. No. Let's make sure that we use semicolons, please. I don't want trouble. Because there's a bit, while you can avoid using semicolons, but there seems to be a big caveat there. A can of issues, essentially. But anyways. Right, so I think we're good. Anyway, let's go back to what we were doing. So what we were doing was we created the bound group, right? Already or no? I don't think we have. Yeah, we haven't yet. All right, so let's create a bind group. So let's create it here. Why not? Bind group is equal to device create bind group. And you just say layout is pipeline get bind layout 0. Did we set up the layout in the pipeline though? I'm not sure. We'll see about that in a second. Next step, you got like a binding 0, and the resource is a sampler. I gotta create obviously the sampler. And here we got like a binding being 1, obviously, and then the resource being a texture.create view. And yeah. All right, so that's that. Now let's make sure to create the sampler, and also let me verify that the pipeline doesn't need any editing. Yeah, there's nothing extra there for the binding group, so I'm not sure. Maybe you're just supposed to say get bind group layout. Okay, whatever. Next, let's see, we got the sampler. So the sampler is device create sampler. And the mag filter obviously just nearest. And min filter nearest or linear, depending on if you want it pixel crisp or you want it to be smudged a bit for smooth textures. But yeah. All right, that's basically that. Do we have the texture already? Did we create it? I don't think we did. So we have to probably call texture is equal to use our checker box thing. Though I believe it's probably an async function though. So we just create checker texture and then we give it the device and the size, but they already have a default one, so that's fine. And I guess that's that, right? Yeah, it's an async function. So yeah, that seems good. create checker texture, and then you got texture. Right. And this is what we got. That doesn't necessarily look like a checker box though, which is interesting. So let's verify if this is right. And let's also give it the shader. Or are we missing something? Bruh, no. Array stride mismatch. Vertex layout sets array stride for x4, but each vertex contains 4 floats. Each is 4 bytes, so retch. Watch. So yeah, I don't think there is a problem. Array stride 16. Yeah, I think the code is correct. But I'm not sure what I'm looking at though. Alright, I guess let's ask it. The nice thing on Gemini, you could just tell it, does this render output looks correct? Because that's not a checker box. The quad is sampling because needs. Okay. Sure. Okay, let's just verify first of all that it actually works. And then we could write it ourselves to make sure we understand each bit. Okay, it works. All right, so there was some issue with that. But can we just try to fix that thing first? Can you just try to fix that canvas way first? Oh, okay. Replace your crate with this updated version. All right, let me just try it out. So see if it works first of all. All right, so this also works. All right, so there was some bug with that AI generated code in the tutorial. All right, sure. So let's see what we got here. So what was the issue exactly? So obviously the same off-screen canvas things, same cell size thing, and the for loop, and create texture size or a norm. And here we just add one thing though, apparently, which is, I guess, maybe just the render attach. Is that really all what's causing the issue here? For real? Yeah, it is. So you just gotta make sure that it's a render attachment. Why? I don't know. And apparently you don't need this extra create image bitmap step. You could just pass in the canvas directly. There you go. Perfect. Perfection. Nice. Why this fixes it? WebGPU relies on the hardware's render pipeline to copy browser. Ah, okay, gotcha. That's why. To copy browser canvas. Okay. So it kind of like basically uses a text, like a shader under the hood to do that. Okay. The copy operation silently fails or generates a validation warning. Direct canvas skip pass skipping. The WebGPU handle the memory transfer. Okay. All right. So I have a few questions. What is image bitmap? And another thing, also explain the checker box math. Is there anything else that I like to know about? Nah, that's fine. All right, so these things are the ones I don't understand. Okay, followed by step-step to checkerbox math. What is image bitmap? In standard browser JavaScript, you can load an image file, canvas, or blob. The pixel data lives in high-level main memory. Okay, high performance, the pixel. GPU ready memory buffer. Asynchronous decoding. So create image bitmap decodes the image asynchronously in the background. Okay. Web worker friendly implements the transferable. It can load and process images in background web worker thread. Checkerbox math explained. The loop that creates a checkered pattern relies on integer division and the modulo operator. Let's break down each operation. When drawing across grids, you need to converge to lock grid cells coordinates. Okay. Oh, math floor. Okay. So it's basically like math floor. Well, that's interesting. All right. Divided by. Okay, cool. Makes sense. Gotcha. The alternating pattern. Plus and. Which returns 0, 1 for even numbers. Okay, gotcha. Yeah, I get it. I get it. What was really confusing me here was this guy. I didn't understand what the hell is this, but apparently just math the floor, which basically just takes like a fractional value, like from 0 to 1, and it converts it into an integer. It removes the fractional part of it. And then you two simply just do modulo 2 and make sure that it's even. And if it's even, you change the color. But what is this y3 equals? It picks white even when false it picks gray. Okay. Okay, the core difference checks both value and type. Checks value only. All right, gotcha. Okay. So this is true. This is true. All right. White space converts to 0. All right, gotcha. Rule of thumb, coming from strongly typed languages. All right, gotcha. Okay. All right, so that was it for that part. Now let's go back into that more. So I guess can't I just draw the checker box grid using Rex directly instead of pixel by pixel? All right, let's see. So yeah, the AI generated code was kind of slow there. As you can see, it basically it started with like just pixel by pixel generating this grid, but apparently you could, since we're using the canvas anyway, we could just use a Rex thing, which should be way faster. So still step by cell size instead of 1 pixel at a time. Right. And check the grid parities and cell coordinates. And draw an 8x8 block directly. All right, that's lovely. So here what you basically do is instead of plus plus, we say plus equals cell size. And here plus equals cell size. And we check the grid parity. Is that the same thing that we were having? Oh, since we're only having the cell sizes, we don't even need this thing anymore because we don't need to floor anything really at this point. And so, yeah. And since that's just a plus, we could definitely just remove these at this point. And yeah. Whoops. Well, instead of just 1 pixel, here we gotta say cell size. And boom. All right, works. Lovely. Next. An even cleaner trick, fill the background plus draw only dark squares. Ooh. Well, that's interesting. So yeah, that's sick. So we could basically just say context dot, well, wait, what the hell? Context fill style is equal to white. There's like 6 F's there, I think. 1, 2, 3. Okay. I think I could probably just use like 3, but anyways. Next up, we got like the fill rect. And you fill rect with the size, so you fill the whole thing with white color, and then you draw only the dark squares. And you do that by simply wait. So we got 1 loop this time. For some, actually we do have 2. Yeah, we have 2. So plus equals cell size, but here they're kind of just basically like calculating the x offset. Huh. Offset x by cell size on odd rows to create. Oh, okay. I see. Interesting. Okay, so every line they kind of like calculate the offset depending on which line it is, right? So if it's even, like you could have an offset of 0, but if it's odd, you could have an offset of the cell size. Yeah. And that would allow you to remove that like parity calculation every single nested iteration. All right, that's pretty sick. So y divided by cell size and modulo 2 is equal to 0. And if it's 0, then we have no offset. Otherwise, you use the cell size as the offset. And obviously right now, instead of starting from 0 in the inner loop, we start from x offset. Right? And then x plus 2. And then we loop apparently by... Wait. So we remove, first of all, this is y thing, I believe. Now, obviously, we set the context fill style first before that part. And yeah, so as you can see, we got those offset now, but we got a jump in cell size times 2. So we could skip those white gaps. Yeah, that's pretty sick, actually. I love that. Yeah, pretty cool, man. So there's this, reduce the draw calls down to just 32 rectangle draws. Isn't this more efficient than even the buffer way? Now that, oh wait, what the heck? Now that we're not writing pixel by pixel, although we have to have the overhead of creating 2D context. Because I think if you want to write one pixel by one pixel, like we were doing before, it would be way more efficient if you just use that buffer way instead of using a canvas that we had in where is it? Wait, so this one is in the context. Okay, so it would have been probably way more efficient if you just used a simple array instead of a canvas. So you just create like a new uint8 array of size times 4, because we have 4 channels. And then you would basically do the same calculation that we had before. And you just say offset is equal to y times size plus x times 4. And then you basically offset by the byte and write the color there. So yeah, and then finally you just... Wait, how do you... Oh, so like instead of... Wait, what? Oh, instead of copy external image to texture, use write texture. I gotcha. Okay, so because like the canvas image is kind of like an external GPU texture, so I think it's even like 0 copy. Yeah, I think so. So this is kind of like, you know, you just import the external image into your context, which is pretty sick if you ask me. But let's see what it said here. But no, the direct array buffer approach is still fundamentally more efficient than the 2D canvas approach. Oh crap, well, it's much more complex than I thought, I guess. Initializes a stateful 2D rendering pipeline, font engines, path bundlers, vector rasterizer. Oh crap. So I guess maybe if you're not going to be doing some very like complex rendering using the canvas, like, you know, text or vectors or SVG or whatever, then you should probably not use it, as you can see here. Internally allocates temporary... Oh, it's not 0 copy. Okay. Gotcha. Yeah, makes sense. All right. Gotcha. In contrast, allocate 16 kilobytes of raw heap memory once. Yeah, I see. So my intuition wasn't 1% correct because I was missing a few details there. Even drawing goes through the browser's high-level 2D layout. All right. Yeah, I gotcha, man. Complex vector graphics, yep, as I said. So you could draw scalable text, dynamic SVG icons, or complex curved UI widgets used as GPU textures. And for prototyping, quickly testing procedural textures without writing custom CPU pixel math. Alright, gotcha, man. Or a compute shader. Maybe we should try a compute shader next, just for the educational value, to be honest. But yeah, this is very interesting. Okay, how to do the array way? I mean, it told me before, but let me just make it regenerate that just in case. All right, so we basically right now remove the context and the canvas. No need for them anymore. And no need for that copy texture, image texture either, but we'll see about that. And we just basically create a data array. So data is a new int each array. Size times 4. Gotcha. And we don't need any fill rect and fill style bullcrap anymore. Yeah, we just go through this the regular way of having to have like, yeah, let's remove this and we'll just go with 0 and just x++ and y++. So the old way, because we don't have fill rect anymore. Though I wonder if like JavaScript have SIMD or something like that. That would be cool. But yeah, we've already kind of wrote this kind of math before, so nothing fancy. Let's just copy it over. Okay, and right now we just calculate the offset essentially. So basically you take a 2D coordinate, like which is an XY pair, and you convert it into a 1D or one-dimensional offset, which you could use on the buffer. And you do that by simply saying y times size plus the x. Times 4, obviously, because we got like 4 channels there. And finally, you just like offset into the data to set the individual channels, which is understandable. Gotcha. Cool. Next, we allocate GPU texture, same format. Oh, but this time we don't even need like the render thing, I think. Yeah, okay. So that's why. All right. That was a bit confusing there for a second, but right now I get it. So, and instead of this, we just say write texture to simply. And we don't need this source canvas anymore. We just write to the texture and we give it the data. And finally, before the width and height, we give it the bytes per row. I'm not getting autocomplete for that, so that's a red flag, but let's just go with it anyway. Rows per image size. Okay, it works. Nice. It works. Lovely. But wait, what's the autocomplete way though? Let's see. So you got like a destination, the data, allow shared buffer source, the data layout. Okay, and the size. All right, cool, lovely. And yeah, that's how you basically do it. Lovely. Next, key takeaways for this approach. Direct access, you allocate a contiguous flat array or block of memory. Oh, you don't even need like async anymore. I don't remember what we were using async for though. Yeah, what we were using async for. Bro, what? Yeah, so we don't need even async anymore for this part. Now I could just, where is that? No need for await. And it works obviously exactly the same. So we need async for two specific operations that return promises into the hood. Create image bitmap when you had in your earlier code was an asynchronous browser API. Oh, okay. So the browser decodes and prepares the image data off the main UI thread, so it doesn't freeze the page because it returns. All right, gotcha. Yeah. I understand. Fine. So if you basically just use the image array bitmap thing, not really the canvas. That was just kind of a left off thing. All right, so we're good now. We're good. So does JavaScript have SIMD or some efficient way to draw rectangles into the buffer, like the canvas way? But without the canvas overhead? That's my first question. The second question is, also, I heard of, what is it called? Yeah, shared buffers. What's that about? Not directly anymore. So JavaScript originally had an experimental SIMD.js API, but it was deprecated and moved in favor of WebAssembly. Can now run explicit vector instructions. However, automatically optimized loop execution. Okay. 32-bit view, uint 32 array. Instead of setting individual bytes one by one, write an entire 32 pixel integer in a single operation. All right. Treat the memory buffer as a 32-bit integers instead of 8-bit bytes. And science times science instead of science. All right, that's pretty cool. ABGR RGBA 32-bit packed integers, little Indian, white and gray. And then you basically go through. All right, that's pretty cool. That's way better. And nothing changes really, I think, here. Yeah. And the option B is the typed array prototype fill. Ooh. Fill a contiguous block of pixels, a horizontal line or row segment instantly. Well, that's interesting. So that's kind of like memset, I think. All right, why start index and then int index? Well, why not use it? And obviously there is the WebAssembly way. All right. Gotcha. The WebGPU rendering pipeline, the catch, race conditions, and atomics. The atomics API. So atomics add. All right, got it. So that's for multi-threading. Okay, so how to use this? In our case, that looks a pretty advanced, optimized or optimal. Oh, we could do the exact way we've done it before using the canvas. All right. So this is the most optimized approach you got so far? I think so. I mean, obviously we could use the compute shader. Yeah, that's another topic, but I'm just talking obviously about the JavaScript way. So generated completely on the GPU in parallel, 0 byte transferred. But honestly, the compute shader have its own kind of overhead of, having to go through with compute shader. But well, I mean, the nice way though is that you don't have to upload the actual data generated. You just do everything in the GPU, which is actually could be faster. I don't know. Next up, we got like uint to reach array fill, fastest JavaScript approach. Cool. Uses 32-bit memory, right? Native C++ memset blocks inside V8, 0 GC pressure, and then you got the uint 8 array pixel loop fast. And finally, the canvas approach, which the AI actually have came up with, which was the slowest. High overhead from 2D rendering engine states, vectorized. I'm pretty sure if I told the AI to use it this way, it would have generated like a much more optimal way, just like we've done here. But yeah, high overhead but like if you don't know JavaScript, then you don't know these ways, then you can't really tell the AI what to do. Unless maybe if you tell it to write performance code, then maybe would have get it. I don't know. Anyways, so high overhead from 2D rendering engine states, vectorization, texture conversions. The ultimate final step, the compute shader. Nice. If you need to generate procedural textures like nose, checkers, or high maps that are even faster, skip the CPU completely or write WebGPU compute shader. So yeah, this is the nice thing about like the modern APIs is that they got compute shaders and they got render bundles and all these sorts of things that it makes the actual language, description language you use insignificant, like its performance insignificant, because you could do most operations on the GPU and you could prepare the whole state in the first frame, and then the actual like JavaScript code that you execute every single frame is the most minimal possible, right? So, which is pretty exciting to be honest. And obviously you get to run it like everywhere, the web, mobile, you name it. Instead of writing pixels on the CPUs and yeah, this is pretty exciting stuff. I love writing fast code in JavaScript. It's pretty cool stuff. All right, so how are we gonna do this now? Let's go back into the code and let's figure out how this works. So basically the first thing is that instead of having a new uint 8 array, you could just go ahead and use a 32 array. And so you remove this times 4 because you're gonna be writing a whole color, a whole pixel in each iteration instead of like writing each channel manually, byte per byte, which kind of suck. Other than that, So now instead of doing this 4 kind of ways of doing things, and even better, you could actually right now store the colors. Like you could say white is basically 0x well, 6 ones, right? So 1, 2, 3, 4, 5, 6, right? So that's your white. And your gray is 0xFF for the alpha, and green, blue, RGBA. Wait, what? RGBA. So I would guess the alpha is the first and the blue second. Okay. So all of them 8, 8 for the gray. So this is the blue channel, this is the green channel, and this is the red channel, I would guess. Yeah, I mean, if you do this, I don't know. We'll see about that. All right, cool. Next step, we do that is odd row thing that we have done before in the canvas way. So is odd row. Wait, hold on. Before that, actually, even you gotta make sure to fill the whole thing with, so data32 or just data dot fill. So you fill the whole thing with white first, and next you basically go through that thing, and for each line or each row you calculate if it's the odd row, and so you do that through y divided by cell size, this and that. Though I think you could probably just I don't know, not really actually, never mind. So yeah, you check if it's odd, and then you calculate the x offset. And so basically if it's odd, then we can use the cell size as the offset, otherwise 0. And then we even got a row offset. Wait, what? Start x offset in row? What does that mean? Row y times size. Oh yeah, so like the row offset in one-dimensional space. Okay. So the row offset is y times the size, which, and that's that. Next step, we go through from the start x offset less than size, and then instead of plus plus, we go through and jump by cell size times 2. Okay. And then we got a start and an end. And now we don't actually need any of this business, apparently. Yeah, this whole business goes away. And now we just calculate the start, which is the row offset plus x. Okay, and the end is start plus cell size. Wait, what is the start? Oh, this one. Oh, okay. I wonder though if that would work. Wait. I mean, let's see. So fill and gray, comma start, comma end. There you go. It works. Lovely. All right. It works. Yeah, because we're going through every row. Oh, okay, so that makes sense. Start plus cell size. And yeah, there you go. Cool. So this is the most optimal way of doing this in JavaScript. So next we could possibly try the the compute way if you want to go even further. But I'm not sure if I want to do that. All right, so let's ask the AI now. And so we could have an excuse to learning some compute shaders too. How to do compute now. To switch from generating the texture on the CPU to a compute shader, you'll create a second shader pass in WebGPU that runs in parallel across GPU threads. Before your render pass execution. Here's how to set up the compute shader pipeline integrated into your code. So you gotta update the shader GLSL or WGSL at the compute shader entry point. All right. So you could basically put even like the compute shader in the same WGSL file or WGSL shader. Cool. I had the impression that I would had to make like a separate one, but apparently not, which is lovely. And then you refactor the main for the compute pipeline. So you allocate the texture. Wait, how I'm doing it currently? Yeah, I'm just using the right texture function. Okay, so here you just create a compute pipeline. You create a new bind group though. And then you create a render pipeline. I wonder if web have mesh shaders. I don't think it does. And then what you do is you go through first of all a compute pass. And then next, the pass B is the actual render pass with the generated texture. She's pretty cool if you ask me. Yeah, pretty lovely. All right, so let me give it the actual WGSL shader that we currently have. This is the current, wait. Yeah, let's start there. Let's start by adding the entry point of the compute. And then we could move on to the actual CPU code. And what the hell? Okay, there you go. It's so slow. So do we change though anything about the current like fragment and vertex shader? No, it's still pretty much the same exact thing that we had earlier when it comes to the fragment and vertex. So those doesn't change at all. What changes though is the compute shader. So for the compute shader, we're gonna have like a group 0 and binding 0 apparently var output texture. Now this one, instead of a regular texture, which is read only, you can't write to it from the shader. Right now we use the texture storage 2D. Right, so a texture storage 2D, and then you give it like the actual format, which is in this case RGB8 unorm apparently. And then you tell it if you want to write to it or read to it, I think. Okay. And then you create the actual compute. Like, wait, what the hell? Compute, and then you say compute main. And obviously you also need to add the work group size though. Work group size, which is h by h. I don't understand how like you set those 8 to 8 or whatever. Like how do you choose that number? But we'll ask it later. But for now 8 would work just fine. And here you say compute main. And then obviously here we could either use the struct as we've done with the vertex and fragment shader, or we could just use it directly as a parameter. And for now, let's just use it as a parameter. Built-in global invocation ID. Unfortunately, the autocomplete is not the best, but fine. Vec3u. So instead of vec3f for floats, we here use vec3u for unsigned integers. Yeah, and instead of like a an F8 or yeah, instead of an F32 texture, which is a float texture, we use RGB8U norm for the actual integer thing, the unsigned integer. Cool. Next, what we do. So we got the cell size. So right now we're gonna write that same like CPU things that we had earlier, but now we're gonna write it in the compute shader. But obviously, since we're going to be writing this in the GPU, which is embarrassingly parallel across multiple pixels, we're not going to be doing that CPU-like optimization for writing individual rects, because that would be actually slower, possibly, I think. But here in the GPU shaders, you just write formulas, math formulas for each pixel, and it's going to be very fast regardless. Because like it's very embarrassingly parallel. You just write a formula that maps a position, or like in this case an ID, to a pixel color for each pixel. So here is white is equal to what? To ID.x divided by the cell size, where the cell size is currently just you know, a constant. And then you got like id.y divided by the cell size. All right, wait. Oh, sorry, wait. Let me just fix that really quickly. In fact, we don't even really need this because that's a plus, bro. So who cares? All right, and then modulo, I think the cell size or 2, actually 2, yeah, modulo 2. Modulo 2u is equal to 0pu, yeah, 0u. All right, so that's is white. Next, we select. So let color is equal to select vec4f. So it's just like the mix function. Is it the same thing, or is it like a binary kind of function, or I don't know, we'll see. We'll have to ask it later. But for now, we just gotta say 0.533. I'm not sure why I didn't use just 0.5 though. That's weird, but we can ask it later. 0.533 and then 1, comma 0, comma, right? And then vec4f. And then we select one of these colors, so either white or gray, depending on that is white argument. And then we texture store. So instead of, yeah, so this is how you write to the storage texture. Use this texture store function, and then you give it which texture you're talking about. And obviously you notice that here we don't need a texture sampler. We just write the raw texture thing directly. And id.xy, which is basically like the position, and then the color that we want to store there. All right, so I have a few questions there, but let's see. So, wait, texture binding, and so we gotta make sure that it's have its storage binding. So the texture binding, because we're gonna be using it in the shader to render to it, like as a, you know, a shader kind of binding in the fragment shader, and the storage binding so we could write to it from the compute. And here in GS, dispatch work groups using. All right, let's just continue the actual code before we start asking it questions, actually. So right now, instead of this whole CPU code to generate the checkerboard texture, we are going to do it in the actual compute shader. So let's see what we got. So I guess right now we could just remove this whole create checker texture function altogether. Bye-bye JavaScript generation. I'm going to use compute. And let's go to where we're creating the allocate So shader module, huh? Where's the shader module? There you go. Okay, so here, I guess, or something. We'll see. All right, so we could create our so size 64, and the texture is device create texture, and the size is obviously size comma size, and the format. And honestly, instead of size, well, fine, just keep it. And the format. Ooh, so the autocomplete actually gives me that. Nice. No need for enums apparently, just use strings. And the format and then the usage is GPU texture usage dot texture binding and GPU texture usage dot storage binding. All right. And why it's, oh, do we have a texture already? Yes, we do here. Okay, so we could remove that. And let's see. So we got the texture. Next, we're going to create the compute pipeline. And so for that, we just create compute pipeline. There's even an async function, which we could look into later. And the layout is auto. And the compute is module. And then you give it basically the shader module. And finally, the entry point. Creating compute shaders is very simple. There's just a few things that is confusing me currently, which we're going to ask questions about soon, which is nice. All right, so that's that. And obviously you gotta create a compute bind group for it too, which you just say device create bind group. There you go. And you give it a layout, which apparently you just get the bind group layout. In Rust, you had to create those bind group layouts manually for some reason. I'm not sure why. But here you just say get bind group layout and it just works. Weird. And then here you got like entries. And the binding is 0, comma the resource is texture create view. And yeah, that's the pipeline bind group, pretty much. Very simple. So is there anything we don't have to change anything honestly about the bind, I guess the render pipeline. Next, what we do is just yeah. So right now, instead of having only like a render pass, like here, which is basically this part here, we're gonna have a compute pass. So let's call it, I guess, the C pass or whichever. And encoder.begin compute pass. And obviously you gotta end it. So basically, wait, what? Oh, sorry, cpass.end. Nice. So basically we're gonna run the compute pass, then the actual render pass after it, essentially. All right, so how are we gonna do that? Well, compute pass or cpass dot set the pipeline to the compute pipeline. Oops, compute pipeline. And then the cpass dot set the bind group to compute bind group. And compute pass or cpass dot dispatch work groups. And then size divided by h, because we set it we divide by h because here in the shader we set it to h for the work group size, and size divided by h here, and we're done. All right. So is that it? Now the real question is, does it actually work? And that's a good question. It doesn't seem to work now for some reason. Oh, I missed some semicolon, I guess. Somewhere. What? Where? Oh, let. Use const. It's not list, it's const. So that's one thing. And error while parsing WGSL expected for variable declaration. What? I have semicolons there. Am I supposed maybe to do it like this instead? Or what? Well, that's weird. You know what? I'm just gonna tell it that. So I fixed the first one myself, which the AI, instead of using const, you use it let for whichever reason. And let's just see what we're gonna do next here. Or we could just search for WGSL compute because the AI is so bugged out, the UI. Compute shader. I mean, that's right, correct, I think. Oh, actually, apparently the workgroup size, I think... Wait. They're doing it like this. Okay, how about this other samples thing? Wait. Is there like a compute shader here? By any chance? There's compute voids. And then we could check the sprite WGSL or something. There's the vertex, nah, this one. Oh yeah, so the work group size is first of all like this. So that's the first thing that I could notice there. The other thing that I could already notice too is that maybe it's supposed to be like this var. I don't know. No, it doesn't seem like it. Wait. Built-in global invocation ID. Nah, that's just the name, nothing fancy. All right, let's go back to the AI here and see. Oh man, hold on, stop it. The UI is so slow, man. Hold on, let me try to reload and hopefully it would improve. And yeah. And let me give it the error that I got. Wait, where's the... Didn't I have the terminal? Okay, there you go. And in fact, this I already changed this anyway, so let's do this. And let's do this. Oh, I didn't? Okay, my bad. But it's still not working. Yeah, I'm using... Wait, what? What? There you go. So you got computer shaders working. Lovely. Let's go, man. Let's go. All right, so let me ask you the questions that I had. So the first thing first is work group size. It seems too random to me. How do you choose the proper group size number? Is 8 just arbitrary? I don't think it is, but... Or what? This is the first question. Second question is select like mix, or is it just for binary values? Or sorry, bool values. This is the second question. The third question is... let's see. The third question. Yeah, and also, and the dispatch work groups. Is 8 just arbitrary? The only thing I know is that multiplying them should give the size. That's the only thing I know. And is select like mixer just for bool values? Okay, what other question I have that I don't get it, that I don't understand? I think the other stuff is pretty understandable, honestly, so far. Yeah, the only thing is git bind group layout. Also, in Rust WGPU, I had to create the bind group layout manually. What's up with JavaScript? That's another one. And finally, the only mild question I still have also is about the group binding things. Also, is it fine is it fine that you're using the same bind group, the same binding in group 0, 0 as the vertex fragment shaders in the compute shader? Yeah, these are the questions I have currently. Let's see. Not quite. It's driven by GPU hardware architecture, hardware reality, warps, and wavefronts. So NVIDIA have 32, and AMD have 32 or 64 threads in each warp, I guess. So if XYZ is a multiple of 32, I mean, don't we have it here? Like 8 times 8. 8 times 8, I guess 64, right? Just to make sure, 8 times 8, 64, I think, yeah. Alright, so it's a multiple of 32. Yeah. This cleanly fills 2 NVIDIA warps, or 1 AMD wavefront, with no idle lanes. Gotcha. So it basically just should be like 64, multiple of 64, or 30, like, sorry, 32. Okay. And the work group size. Local layout within a single thread block. For 2D texture, 2 shapes like... Alright, gotcha. Gotcha. Oh, so it's a ternary operator. Alright. Yeah, gotcha. Okay, okay, okay. So the mix is like lerp, right? But select is for boolean, or even vicbool, which is like mask apparently. All right. Oh, so nah, not mask. It's like for components. So which components you're gonna use or select? Okay, so Rust WGP manual layout, VSGS auto. Oh, so the actual, I see, it just generates the group layout for us. All right, lovely, through reflection. Nice. Passing the same camera matrix uniform to 10 different shader materials. I mean, you can't reuse bind groups right now, or what? And is valid, okay. Okay, so the compute pipeline is separate from the render pipeline. Use inferred layout from A. Okay, so it's kind of like just a way to make sure that they're using the same layout. Yeah. It fails if the shader binder differs even slightly. Expects a sampler and pipeline B expects T texture 2D. Okay, gotcha. All right, I get it, I get it, I get it. Okay, why we have groups? I think it's probably because of updates. Why we have multiple groups? And when do we separate into groups? I think it's probably the update rates from what I've researched before, but just making sure. We have multiple group slots, primarily for frequency, yeah, of updates, performance, and material engine organization. Changing the bind group on the GPU is an expensive operation. If you lump all your data, camera, object, position, texture, lighting into a single bind group, you have to rebind or re-upload everything every time a single object moves or changes material. Yeah, so you basically group them by frequency of updating. So by splitting data into separate groups based on how often that data changes, game engines minimize driver overhead. So your per frame data, it updates once per frame, it goes into the group 0. So the camera view, projection matrices, sunlight time, you get it. Next up, you got like group 1, for example. You could put there the per pass material stuff. So like updates per material shader swap, albeit the texture, roughness sampler, shader parameters. Next up, you got the second or third group actually, if you're starting from 0. It's the per object data, updates per draw call. So the model world, transform matrix, entity ID, dynamic colors. So this is how a typical render loop handle these groups. So your frame start, you got set bind group 0, frame bind group. Then you got every material, you set the bind group 1 to the material bind group. And then for every object in the material objects, you set the bind group 2. Okay. Yeah, that makes sense. So GPU cache persistence. When runs for 5 different meshes. Okay, gotcha. I get it. Yeah, I kind of knew this stuff, but just making sure. Okay, so the limit is 4 bind groups apparently per pipeline. Group 0 through group 3. One group fine for simple apps, full screen quad effects, or procedural text generation. And 2-3 groups standard for 3D engines. Yeah, that's pretty sick actually. Lovely. All right, so I love this actually. It's pretty sick stuff. So I think we could split this up into multiple functions so it's clear what the hell is going on around here. So up to this point, we basically just kind of like, I mean, here we kind of like just created the device and the adapter. Next up, we got like the canvas and the context and the format and context configure. So like the canvas is a bit like a window to some degree, right? So that could be separate. So we could basically group this into its own function, for example. Honestly, this one is just a check that you do once at the start. So this one is for checking for support, essentially. So you could say that function check WebGPU support. Ensure WebGPU support. Yeah. And you just do this. And now I could just call ensure WebGPU support. So this is what we have here. Next up here, we got like the actual kind of GPU thing. And I think I didn't even use the adapter anywhere here other than creating the device. So, okay, I guess for now at least, we could call this, I guess, create GPU or whichever. And you just return the device. And here, obviously, this should be async. And then you just say await create GPU. And yeah, or like create device if you'd like. Doesn't matter the name. We don't need to store adapter. I mean, since we're in JavaScript, this is reference counted, so we don't gotta worry about the adapter going out of scope or whatever, as long as we don't need to use it. But yeah, anyways, so that's your device. And next up here, we got the canvas, the context, the format, and these things. Get preferred canvas format. Wait. Okay, so this is just for now. All right, cool. So what we could do for this part is just like you kind of create a context essentially. So async does it need async? I don't think, no. Create context and you kind of just give it like the canvas ID. Yeah. And you just have that, and then you just pass in the canvas ID here. And you just configure. Pretty much. So right now, instead of this business, you could just say create context, I think. Wait, am I using the canvas at all? Well, only for that part, I think. And finally the context for that part. I'm not even using the context though, like, so I could probably just say this. Wait, do I? No, I probably am using the context somewhere. Hold on. Yes, I am using it to grab the current texture. Okay, makes sense. So, yeah, so I should return the context essentially from here. And then you just remove this business right here. Well, that whole thing, and then you just say create context and then the ID of that canvas or whichever. Oh, and why the hell? Whoops, where did it go? Device is not defined. Oh yeah, sorry. So you do need the device, I guess, here. No? Yeah, you do need it to configure the context. Yeah, all right. So configure. Sure, let's give it the device. And then here is supposed to pass in the device and the ID of the canvas. But it still not works. Why? Format is not defined. What? Oh, I think we're using it somewhere else. Okay. Can't I just grab that from the context somehow? No? I don't think. So we'd better just say const format is equal to this. I mean, yeah, just copy this part and remove it from here. And you just add it there. And finally, you just pass it in here. And boom. And yeah, that's... Wait, why do we still have the adapter thing here? Yeah, we could just remove that part, actually. Ensure that WGPU supports, create the device, grab the format, and create the context. And then you load a shader, and you even create a shader. I mean, I'm not using this thing anywhere here. So I could just do it in one step, to be honest. Like I could just say, have an async function called create shader, which you just give it like the what is it called? The URL or whichever. And then you just do this 2 steps in one step, essentially. And then here, just give it the URL. And so this is like the source, or the code, shall I say. And this is the module. And you just return that module, really. And now here, instead of doing this, you could just say shader module. Whoops. Is equal to, instead of load shader, create shader. And you're good to go. Wait, why it failed? Oh, I need the device. Okay. And what else? So next we got creating a texture. You just kind of like give it the size, the format, and the usage. Nothing fancy there. Next you create a pipeline. And then a bind group. Another pipeline here. Yeah. And yeah, that's basically that. right? Create command encoder. I mean, we could put these into functions too. Like, for example, here the compute pass stuff, could put it into its own thing, I guess. Begin the compute pass. I mean, what this uses the compute pipeline, which obviously should be created once. Same thing with the compute bind group. And finally, the size of the texture. But honestly, no need, I guess. I don't know. And this is for the actual rendering part. But yeah, you could have like this into its own function. Fine. Like function render, and let's see what we're gonna need there. So we're gonna need the, well, first of all, the actual view or like context or whatever. Well, just you could just pass in the whole context, in fact, but I mean, no need, or isn't it? Like, what do we use in the context for? Yeah, only just the view. Okay, so let's just grab only the view actually. The view, and the clear value too. So let me just do this, and the clear value, same thing, and we just pass it as like this. Well, actually like this, and honestly we could just call this clear color instead. Next we got this, that, and the pipeline. So we're gonna need the pipeline too, obviously. So fine, let's just pass in the pipeline here, and the bind group and the vertex buffer, and the vertex buffer, and how many times you're gonna draw that stuff. But yeah, that's that. So these kind of like the resources essentially. In fact, I should make this into a struct hopefully. How can I make a struct in, or a class in JavaScript to bundle? So these are like the render resources. Oh, so this would basically like, I see. Interesting. Interesting. All right, I love that actually, like that. So let's see how we could do that. So we could create a class, and I don't know what I'm gonna call this. Let's maybe say render pipeline, I think, for now. And then you got like the constructor, which takes in a device and the shader module. Shader module. I mean, just create the shader there though. Yeah, just create the shader there. Same thing I believe with texture, maybe, and sampler, etc. I think, or isn't it? Well, for now, let's just keep it simple. Let's keep it did simple. So we're just gonna contain these three guys, basically, for now. So you just, do we even need the device currently? No, we don't. So you just pass it like this, and then you set it. So this dot pipeline is equal to pipeline, and this dot what is it? Bind group is equal to bind group, And this dot vertex buffer is equal to vertex buffer. And what else? Yeah, I think this is it for now. And then instead of doing this, I believe we could just grab the render pipeline essentially. Or sorry, not pipeline. For now, we could call it just resources. Resources, right? Render resources. And how would this work? So now we could just say resources.pipeline, resource.bindGroup, and resource.vertex buffer. Yeah. Okay, cool. Now what we could do is we could copy this part really quickly here. And we can come here and we could remove the, yeah, I think I've already removed it. So yeah, and let's just comment this out. And here what we're going to do is we're going to create resources, render resources. The real question is, how do you do that? I think probably, so render resources is equal to probably new render resource, I would guess. Yeah, there you go. Then you just give it the pipeline, the bind group, and the vertex buffer. And judging from those, I think you're supposed to do it like, name it like this. So that's your render resources. Next, you just call render function. And here, the view is basically context.getCurrent texture create view. And the clear color is this guy. And finally, the actual render resources is that. Now let's see if there's any errors. Encoder. All right, so I forgot about the encoder. Okay, sure. And we need obviously the encoder too. And so we gotta pass that too. And as you can see, that works. Awesome. All right, so and the compute pass, we could do a similar thing essentially. But yeah, though I would love if we just right now make this more interesting by just putting everything when it comes to render straight into the function, into the class itself. So like, I think we could just, let's see, sampler bind group. Yeah, we could just grab this whole thing, I believe, like vertex buffer, the cloud vertices, the pipeline, except for the compute stuff, obviously. Could take that whole thing and come to our render resources and just do this. And now we don't need to take any of these, right? So like pipeline, bind group. Do we have the bind group here? Yes, we do. And the sampler. Yeah, that works. We need one thing though, is the device, obviously. That's one thing. The other one would be the texture, I think. Where is the texture? We're using it here, yeah. So like the view texture. So could call that view, I guess. Other than that, we're pretty much good to go, I think. And we need to pass in the shader module. But yeah, let's just grab that view. And where's the shader module? Well, actually, we do need the shader module too, yeah. So let's grab that. And anything else? So now instead of passing in this, guys, we pass in the device, the shader module, and the view. And the view is basically the texture create view, too simply. And then what we could essentially do is also, instead of having a render function like this, we could grab this, remove this, and have a render method instead. So like function render. Right, and then here, whoops, wait, what? What's going on? Oh, a method. How do you create a method? Oh, you don't need to say function. All right, cool. So begin render pass, color attachments. We're gonna take in the view obviously every time. The clear color for now, that's I guess fine. Next step, we got the resources pipeline. So instead of resource pipeline, we say this. Okay. So this. And now we're gonna set those there. So this dot bind group, right? So and this dot sampler. We do need the sampler, right? Actually, not just inside of here, so that's fine. And the vertex buffer. So this dot vertex buffer. Or yeah, fine. And next step, we got this pipeline. This dot pipeline. And I think we're good to go. So is it even called it rendered resource at this point? Yes, it's still called render resource. Let's call it, I don't know, render pipeline, yeah. And let's create that render pipeline. And now we could say, oops, let's call it render pipeline. And then we could say, wait, what the hell? No, render pipeline. Like this. And then render pipeline dot render, I think. And it just requires only the view. Well, also the encoder though. But no render resources anymore because it's the render resources. But we still need an encoder, obviously. So where do we put that? Here. And yeah, we don't need these comments anymore. And yeah, you just got like a view, encoder, view, and clear color. And that works, I think. So now let's see what are the errors that we have made by refactoring this. Format is not defined in the render pipeline. Okay, gotcha. So for the format, I think we're probably only using the format there though, isn't it? Well, can't we grab the format from the view? Yeah, I don't know if that's the case. Can you do that? I don't know. So let's just grab the format too, fine. And then when you create the render pipeline, you're supposed to pass in the format of the texture too. Though I could, hold on, let me check really quickly. So if you create a view, can you grab the format? I'm not sure. I have to see if the API supports that. But anyways, now let's see what other errors we have now. Pipeline is not defined. Where? Pipeline, this dot bind group. Yeah, makes sense. So we got to use this dot pipeline. And boom. Okay, so there you go. Pretty sick. Sorry. Yeah, pretty lovely. And I think I could probably put this right now into its own little script, but yeah. And ensure WebGPU support, load shader, create shader. Now we could do the same exact thing for the compute pipeline. So class compute pipeline, and you just do a constructor, apparently. And honestly, instead of render, maybe we should call it apply, or yeah, fine. We could call this compute basically. And obviously, it's gonna need the encoder. That's definitely a thing. And pretty much the texture, I think. Yeah. All right. So let's see. So we're gonna grab this this guy right here, I think. Yes. And you're gonna put it here. You begin the compute pass, and then you say this compute pipeline, this dot compute pipeline, and this dot compute bind group, or too simply this dot pipeline and this dot bind group. Well, I think bind group like this better. And you also need some size, apparently. Well, for now we could just pass it like that. Okay. And then we're just gonna grab these compute pipeline stuff. The texture is shared between the pipelines, so that's something. And the shader module, same thing. So let's just grab only these for now. And here you gotta say this dot pipeline. Same thing here, this dot pipeline, get bind group layout. And instead of texture create view, you just grab the view from the caller, and get bind group. Bind group. Okay, so here we just say this dot bind group. And obviously we need some few things. We need the device and the shader module, and a view, and possibly even format. We'll see about that. We don't need the format though, right? Yeah, I don't think so. So you just need the device, the shader module, and the view. And finally here in the compute, we don't actually need the view. It's just like the encoder and the size. Though obviously, since we're passing in the view in the constructor, we could just pass in the size too, why not? So this dot size is equal to size. And here we could just use this dot size. And we could just like hopefully rename this to just pass. And yeah, that's that. Next up we got like encoder begin render pass. Okay, that looks cool. Now what we're gonna do is we're gonna remove this whole business, and we're just gonna like say const compute pipeline is equal to new compute pipeline and the device, comma the shader module, and the view. So the view here is basically our texture. I'll create view. Okay, and then finally the size. And basically before the render, and honestly, like we create all the pipelines first, just like this. And then you go ahead and say before the render, say compute pipeline dot compute, and then you give it the encoder, and boom. So you see what we have right now? Pretty cool stuff. Though the encoder here, and yeah. So you just create the resources, the device, etc. You got your pipelines here, and every frame you basically just do this part right here. So like this is the whole frame essentially. So what we should call this though, maybe we can call it frame, for example. Render frame. Currently we're only rendering once. We gotta look into how we could do it multiple times, but yeah. So how this would work, we're gonna have a function called render frame, and it would contain this stuff, I think. Now obviously we need a few things. We're gonna need the device and the compute pipeline and render pipeline. And the context. Yeah, that's also something we need here. Or instead of context, you could just grab the the view. So device and view and compute pipeline and render pipeline. So, and here in the render frame, you could just pass in the device, and the view is basically your context.getCurrentTexture, I think. Or what was it? Like context.texture? Create view, I think. Yeah, I believe so. And then finally the compute pipeline and the render pipeline, if I'm not wrong. There's some error. Yeah, how do you... I think you say get current texture or something like that, if I remember. There you go. Okay, that works. Lovely. And yeah. So yeah, that's basically that. And I think we're good. And this is kind of like just initialization part. But yeah, so alrighty. I wonder though if we could make like some sort of a stack of pipelines, or like apply in a list of some sort, just as a educational thing. How can we make some abstraction that chains pipelines together? So type compute and run encoder compute pipeline.compute encoder. And then you return this allows method chaining. All right. And add render. And for each stage, you could run that. All right, gotcha. So that's pretty cool. So yeah, so I think I'll probably stop the stream here at this point. It's already like 4 hours. All right, so see you guys. See you later. Goodbye.